Hey guys, just a quick message on what this video is about. This is a short introduction into color theory and how it can connect to the Fibonacci and Lucas numbers. You don't need to know anything about graph theory prior to this. And if you guys like what you see, remember to like and subscribe and comment on any questions you have. By the way, the 1997 paper on this is in the description as well as the full image of the whiteboard. All right, see you guys later. Let's just get into the basics. So we call these dots vertices, and vertices can be colored a color. And so we represent usually an edge as a simple straight line connecting these two. Here's my edge. And also sometimes we assign a variable to the whole graph. A graph is a set of vertices and a set of edges connecting vertices. This is a general graph. Today I'm going to be looking at two particular family of graphs, and we represent the stages of the path graph as P sub n. For example, P1 is a single vertice. P2 are two vertices connected by a single edge. P3 is three vertices connected by two edges. A path graph is simply a graph of n vertices that are connected in a line. The other type of graph that I want to talk about is called the cycle graph. The cycle graph is usually represented by C sub n for the nth stage of the cycle graph. And we could have a cycle graph for three vertices. We put the three in the form of a triangle and connect them in one big loop. For C4, we put them in a square. So really what cycle graphs are doing is that they're forming a large loop of n vertices. C2, you will have a cycle graph if you have two edges connecting the same two vertices. And in fact, you can even have a C1, where you have one vertice connecting itself. Now with that out of the way, we're going to be coloring in a very particular fashion. We are going to do 1-1 coloring. And the rules of this coloring is that we only have the colors red and white. So every vertice must be either red or white. However, there's a certain rule. No two vertices that are connected by the same edge can be red. If I had two connected vertices like so, one of them could be white and the other could be red. However, it is illegal if both vertices are the color red. White vertices can be connected to any other vertice, no matter what color. They can almost be described as a sort of wild card color. Could be connected to white. Let's try out this 1-1 coloring with these path and cycle graphs. Let's first do the path graph. P1 could either be white or red. So P1 has two ways you can color it. Remember, we're finding the number of ways we can color. P1 is equal to 2. Now P2, both vertices could be white, and that's perfectly legal. One vertice that is white, while the other is both vertices cannot be red at the same time. So we say that P2 has three ways you can color it. And now let's look at P3. How many ways could you color P3? How many ways are there to color P3 and P4? Maybe take a pause. If you count it correctly, you'll notice that there are 5 ways to color P3. Here in P4, let's take a slightly smarter approach other than just guesswork. How many times can P4 be colored with 0 vertices that are red? Well, there's only one way I can see. How many ways can you color P4 so that only one vertex is red? Well, there are 4 vertices, so 4 ways. How many ways can you color P4 so that there are exactly 2 vertices? Well, there's 1, 2, and then a third way when the red vertices are at the opposite ends of P4. So 1 plus 4 plus 3, that gets us to 8 total ways to color P4. And perhaps you've noticed a kind of pattern in this Pn. You might notice that P3, that 5, is a sum of 3 and 2. And that 8 is the sum of 5 and 3. It seems like the number of ways to color the next higher level path graph is the sum of the previous 2 path graphs. We might conjecture the number of ways to color Pn is equal to the number of ways to color Pn minus 1 plus the number of ways to color Pn minus 2. That is our conjecture. This relationship has a clear connection with the Fibonacci sequence. The Fibonacci sequence is a single sequence of numbers beginning with 1 and 1, such that the next term is always the sum of the previous two. So if we start with 1 and 1, our third term must be 1 plus 1. Our fourth term is 1 plus 2. Our fifth term is 2 plus 3, and so on. The nth term of the Fibonacci sequence is usually represented by f sub n. And we can generalize this relationship in the Fibonacci sequence by saying that fn is equal to fn minus 1 plus fn minus 2. That the nth Fibonacci number is the sum of the previous two Fibonacci numbers. We can see that between the Fibonacci sequence and the path graphs, that the number of ways to color them, with this pattern, we might say that P5 could have 13 ways to color it. Let's take a look into the cycle graph. How many ways can we color the cycle graph? With C1, we could color only one color, because remember, if we did try to color C1 as red, that red is connected by itself through this one loop. You're connecting red and red together. That's illegal. C1 equals 1. What about C2? C2 is very similar to one of the path graphs above. We can color it one way with 0 red colors, and then we can color it two ways with only 1 red color. And that brings us to a total of 3 ways to color C2. What about C3? We can see that there is 1 way to color C3 with 0 red colors, and 3 ways to color it with 1 red color. So we say that C3 is equal to 4 because there's 4 ways to color it. And we can continue this process. So C4 can be colored 1 way with 0 colors, 4 ways with 1 color, and 2 ways with 2 colors. So C4 is equal to 7. Now for the pentagon, there's 1 way to color it with 0 colors, 5 ways to color it with 1 color, 5 ways to color it with 2 colors, 0 ways to color it with 3 colors still. C5 is equal to 1 plus 5 plus 5, that's 11. And now we can see once more there is a recursive relationship here. You C3 is the sum of C2 and C1, C4 is the sum of C3 and C2, and so on. So we may conjecture Cn is equal to Cn minus 1 plus Cn minus 2. But clearly this is not the same thing as the Fibonacci sequence, no, but we started 1, 3. Now this is the Lucas sequence. The Lucas sequence is very similar to the Fibonacci sequence. Each term in the sequence by L sub n, but the difference is that we begin with 1 and 3. So after 1 and 3 comes 1 plus 3, then 3 plus 4, then 4 plus 7, and so on. And we represent the recursive relationship such that each term ln is the sum of the previous two. So by this pattern, we might conjecture that C, the hexagon graph, might have 18 ways you can color it. I'm now going to show you a coloring tool that might be helpful on our endeavors to rigorously prove that the path graphs really do lead to the Fibonacci sequence and the cycle graphs to the Lucas sequence. I'm going to call this the deletion tool. Suppose we started with a specific example, P6. We pick an edge E, and I'm going to delete it. When I delete it, I get 2 disconnected graphs of 4 vertices and 2 vertices. And you might recognize the first one as P4, the path graph of 4 vertices, and the second one as P2. And because they are disconnected, the number of ways you can color this whole graph is the number of ways you can color P4 multiplied by the number of ways you can color P2. Now, there's a problem with this. We can't simply have an equal sign like this because we've actually missed a case. In the case where these 2 vertices are both red. If those 2 vertices are red, then in the original graph, when the edge was there, that coloring would be illegal. So we have to subtract, we have to take back those configurations that make those 2 vertices red. And this time, it's the same graph as just before, but we're considering the cases only when these 2 vertices are colored red. We know that these two next vertices must be white. That leaves no vertices on the right side and just two vertices on the left side, which we can color however we want. So the two colors on the left side, they represent a path graph of length 2. There's two vertices. While on the right side, there are 0 vertices, and we can represent that as a path graph of 0 length, which is equal to 1. P0 is equal to 1 because there's only one way to color it. So when we generalize this deletion tool, we might represent it by the following notation. We have G, our original graph. The number of ways to color G is equal to the number of ways you can color G without E. The case where we need to go minus the overcounting, which is when, and you might notice that on the right side, when we are coloring these two vertices red, we are forcing all of the connections to these two red vertices to be white. Effectively, this means that we could equivalently represent the right graph over here as if it was without the red and white. We define this something called a link. The link of edge E is a graph of the edge plus the vertices connecting the edge plus the vertices connected to the vertices. For example, if this was my edge E, and then I had some graph, then the link E, which we are deleting in this second part over here, includes these vertices and all the vertices connected to these vertices, all of this. However, note that after you remove link E, there may still be some vertices left over. So link E only includes the vertices connected to the vertices of the edge. If I wanted to find the number of ways to color a cyclograph in C4 with this new tool, I might select an edge E and then remove it, so that becomes this. And so these are just 4 vertices connected to each other in a line. This right here is the same thing as saying P4, the number of ways you can color P4. And then remember, minus G minus the link. We're coloring the two vertices connected by edge E red. If we color them red, then we know the other two vertices are white. You're removing the link of E. And what's included in the link of E are the two vertices and the vertices connected to the vertices. So you're basically removing everything. Everything gets deleted. There's nothing left. So because there's nothing left, that'd be the same thing as saying that it's P0. And we could simplify this even further. How many ways are there to color P4? There are 8 ways to color P4, meaning that the number of ways to color C4 is 8 minus 1. C4 is equal to 7, which is indeed true. The second tool I want to give to you is called the coloring tool. We start off with a graph. Let's say we have C5. And we're going to say, I wonder how many ways I could color it by choosing the color of a certain vertex. Remember, a vertex can either be red or white. So let's take the first case. Let's say our vertex is white. And so what this basically means is that we can color the other 4 vertices. We can color the whole graph without V, anything. That is the same thing as saying that's the number of ways to color P4. And then we have our second case, which is when the top vertex is colored red. And if it's colored red, then those 2 adjacent vertices must be colored white because 2 reds cannot be together. And that leaves us with only 2 free vertices in a straight line that we can color however we want. So P2. And let's generalize this. Remember, whenever you have a white colored vertice, you can basically ignore it in the graph. So we started with a general graph G. Once you pick a vertice V, the number of ways you can color it with ignoring V plus the number of ways you can color it when it's red. And when it's red, this vertex makes all its neighbors, it makes all the vertices it's connected to white. And remember, when a vertex is white, you can basically ignore it in the graph. We're cutting out the link of V. The link of V is the same as the link of an edge. The link of a vertex this time is when you subtract not only the vertex, but also the vertices connected to that vertex. So the link of V in this situation are these top three vertices. So recall that our goal is to prove that the path graph leads to a Fibonacci sequence and the cycle graph leads to the Lucas sequence. So first, let's use the coloring tool to find at least one of these. Let's start with the path graph. Let's say we have P5 and I'm labeling the end vertex V. Now I'm going to be using the coloring tool for this one. So first I'm going to color the vertex white. The vertex at the end can be ignored and we have 4 vertices to work with. And the 4 vertices are in a line. The 4 vertices can be colored however they want. The 4 vertices, the number of ways to color that is P4. And then we have our second case where the end vertex is colored red. That means that all the vertices connected to that end vertex must be white. And remember that white can be ignored because it's a wild card color. That leaves me with P3 ways of coloring. And look, we have our recurrence relationship where P5 is equal to the sum of the previous 2 path graphs. Generally, if we had Pn and labeled the vertex at the end V, then this would lead to Pn equals to Pn minus 1 plus Pn minus 2. And here we have our recursive relationship. Because P1 has 2 ways of coloring and P2 has 3 ways of coloring, the number of ways to color Pn is equal to the nth plus 2 Fibonacci number. Okay, well, what about the Lucas sequence? Can we prove that the number of ways to color a cycle graph are the Lucas numbers? For this, we're going to need to use both of the tools. First, let's use the edge deletion tool. Suppose we had C5. Then according to our edge deletion tool, we delete one edge. The number of ways to color that is subtracted by the deletion of the link of the edge. The number of ways to color C5 is equal to the number of ways to color P5 subtracted by the number of ways you can color P3. In general, if we had a cycle graph of size n, then that would be equivalent to the number of ways you can color a path graph of size n minus the number of ways you can color the graph without the link of the edge. So in this case, we would be deleting 4 of these vertices as they are part of the link of the edge, E. Thus, the number of ways you can color C5 is equal to the number of ways you can color P5 subtracted by the number of ways you can color P1. In general, if we had started with a cycle graph of size n, the number of ways you could color that cycle graph would be equal to the number of ways you can color a path graph of size n minus the number of ways you can color a path graph of size n minus 4. Now we are going to apply the coloring tool to the same graph. Suppose we had C5. And the number of ways to color this when V is white leaves us with 4 vertices connected in a line. So that is equivalent to P4 plus the number of ways I can color it when V is red. In other words, when you do not have the link of V. Thus, the number of ways to color this graph when V is red is P2. In general, if we had a cycle graph of size n, then the number of ways to color it would be equal to the number of ways to color Pn plus the number of ways Pn minus 1 plus the number of ways to color Pn minus 3. So we have 2 formulas. Now somehow we want to combine these so that we get the relationship that Cn plus 1 is equal to the sum of the two previous Cn. I'm going to label these equations 1 and equations 2 and use them with their respective numbers. So first thing, I'm just going to write equation 1 with Cn. And then let's write down equation 2 such that n becomes n minus 1. So if you had a cyclograph of size n minus 1, then that would be equal to Pn minus 2 plus Pn minus 4. And you can see when you add these two equations together, we have Cn plus Cn minus 1 is equal to, these two cancel out, Pn plus Pn minus 2. And we can see from equation 2 that when n becomes n plus 1, the cyclograph of n plus 1 is equivalent to Pn plus Pn minus 2. So all I'm doing to the equations is I'm shifting, and so now we can clearly see that this value here is the same as this value. Thus, we have the relationship that the sum of the previous two of the cyclographs is equal to the sum of the next term. Because C1 is equal to, because there's only one way to color the first cyclograph, which is the first Lucas number, and there's three ways to color the second cyclograph, which is L2, we can finally prove that the number of ways to color a cyclograph of size n is the nth Lucas number. So with this information, we can start drawing relations between Fibonacci numbers and Lucas numbers. For example, from equation 1 here, we stated that the number of ways you can color a cyclograph of size n is equal to Pn minus Pn minus 4. Now, convert both of those into Lucas numbers and Fibonacci numbers, and we actually have that the nth Lucas number is equal to the nth plus 2 Fibonacci number minus nth minus 2 Fibonacci number. And you can find relations like this all over the place, these being proven completely graphically through our colorings. If we take equation 2, we proved that Cn is equal to Pn minus 1 plus Pn minus 3. Now convert that into Lucas numbers and Fibonacci numbers, and you have the nth Fibonacci number is equal to the sum of the nth plus 1 Fibonacci number plus the nth minus 1 Fibonacci number. And you know, we could prove even more Fibonacci identities. For example, a really easy one to prove using our coloring system would be to show you this. So suppose that we had a general graph with R vertices and S vertices here with an extra one right here. So the number of ways to color this path graph would be P sub R S plus 1. Okay, and then we're going to use our coloring tool. Now, if the middle extra vertice is white, then we have two disjoint path graphs, one with R vertices and one with S. The number of ways to color this would be the number of ways to color the R side times the number of ways to color the S side. Furthermore, if the extra vertex was red, with the middle three vertices centered around the extra would be deleted since we had to remove the link of the vertice. And we are left with two disjoint path graphs, one with R minus 1 vertices and the other with S minus 1. So the number of ways to color this is P sub R minus 1 times the number of ways to color this other graph over here, P sub S minus 1. And there we have it, another identity. When we convert this into Fibonacci numbers, we find F sub R plus S plus 3 is equal to the Rth plus 2 Fibonacci number times the S plus 2 Fibonacci number plus the Rth plus 1 Fibonacci number times the S plus 1. And we can further make this a lot simpler. Let's substitute R minus 1 for R and S minus 1 for S. So our final identity becomes the r plus s plus 1 Fibonacci number is equal to the r plus 1 times the s plus 1 Fibonacci number plus the r Fibonacci number times the s Fibonacci number. This gives us some like more specific formulas. For example, if r equals s equals n, then we actually have the 2nth plus 1 Fibonacci number is equal to the nth plus 1 Fibonacci number squared plus the nth Fibonacci number squared. And we can still go even further. If we take the almost the same example, we have a path graph of length r and s vertices this time. There's no extra vertices this time. And this time we're going to use our edge deletion technique. We started with p r plus s, and I'm going to delete the middle edge. And that will leave me with two disjoint graphs of r and s. That should be equal to pr times ps minus the graph, number of ways to color the graph without the link of the edge. The link of E here in this example removes all four of these middle vertices. That leaves us with a path graph of length r minus 2 because 2 vertices were subtracted from the r side, and a path graph of s minus 2 on the right side. This makes us subtract by pr minus 2 times ps minus 2. Converting to Fibonacci, we have fr plus s plus 2 is equal to fr plus 2 times fs plus 2 minus fr times fs. And then we can, let's say r is substituted for r minus 1 and s is substituted for s minus 1. We can tidy up this just a little bit. And this becomes f sub r plus s is equal to f sub r plus 1 times f sub s plus 1 minus f sub r minus 1 times f sub s minus 1. Fantastic. When r and s are both n, f 2n is equal to f n plus 1 squared minus f n minus 1 squared. And there are many more identities you can prove. And the fun just doesn't stop here. You can prove so many identities about the Fibonacci numbers and the Lucas numbers and their relationship just purely through coloring graphs. It's kind of crazy. So here I've listed out a few of my favorite identities, which I've done it so I can approve of them. And they're all very challenging, but after a simple application of the two tools we've used, these should become simpler. And the fun just doesn't stop there. In a normal path graph, you'll see a string of vertices. But now, what if each vertex is actually a cycle graph of length 2? So we have two vertices connected to each other, and then they are linked up parallel like that. So maybe here this would be like B3 because there are 3 sets of 2. And over here this would be B4 and so on. Could you perhaps form a new rule based on pairing vertices like this? And another configuration of this could be a cycle graph. And so we can keep exploring. For example, do our box graphs have a recurrent relationship? Meaning, are the number of ways you can color them based on previous stages of the boxes? If so, can you find the recurrence and then prove the recurrence? So why not extend your observations? Explore, have some fun while you're at it. And in particular, you might find something interesting. So I hope I taught you guys something really cool about the connection between Fibonacci, Lucas numbers, and coloring graphs. I really think this is an amazing field. Color theory is amazing. There's so much more to it. So if you liked it, consider subscribing, and see you next time.